All right. So welcome to the one uh, World Minds seminar for this week. I think it's this last talk for the series before we take our December break. It is our pleasure to have with us Yan-Shuo Tan from the National University of Singapore. So Yan-Shuo is from the assistant professor at the Department of Statistics and Data Science. He got his PhD in mathematics in University of Michigan and followed and then did a postdoc after that at UC Berkeley. Yan-Shuo does a lot of interesting work in statistical machine learning theory. I think they have a big focus on decision trees. And part of the reason why I invited him was that he does very interesting, very provocative questions in decision trees, sort of like it takes a very interesting angle. Maybe you will hear more about this today. So, Yan-Shuo, you can take over now.
All right. Yeah, so thanks for the introduction, Yongsheng, and thanks for the invitation to speak at this seminar. And thanks to everyone who's here. Yeah, so it's Thanksgiving, so I'm thanking a lot of people. Okay, so today I'm going to talk about this recent work that I did with the same title, so you can find this on arXiv. And this is this is joint work with my wonderful collaborators, Krishna, who's at UC Davis, and Jason, who's at Princeton. Okay, so this work is about trees and tree ensembles. And I'd like to start with the slide, which is about deep learning. So we know that deep learning is very popular, and lots of people are very interested in doing work on deep learning. And so when this paper came up in NeurIPS 2022, it generated a lot of interest. And so what this paper did was to compare tree-based methods like random forest and XGBoost against popular neural network architectures and examined their relative performance on some benchmark data sets. The takeaway is spoiled by the title. So they looked at 15 classification data sets, 19 regression data sets, and across the board, the XGBoost random forest performed far better compared to the deep learning architectures. All right. So for this particular types of data sets, medium-sized tabular data sets, it seems that tree-based ensembles are better than deep learning. And this is not a new observation, actually. So if you go back in time to 2008, there was already a paper doing this comparison between the different methods, and this also included more classical machine learning methods. All right, so here the conclusion was that random forest was the best-in-class predictor. Here's another paper from 2014, this time comparing 121 data sets and more than 100 models. Again, random forest is the best-in-class predictor. Here's yet another paper from 2018. Again, a lot of data sets, a lot of models. So the best predictors in this case were random boosting random forests. So this observation is quite replicable. So it seems that for moderate-sized tabular data sets, tree ensembles perform the best. Okay, so that's one reason to care about decision trees and tree ensembles. So they have this state-of-the-art accuracy, but there are also other reasons, right? So another reason is interpretability. So what does this mean? So if you take a decision tree, it can be easily visualized. So you can draw the tree structure on a piece of paper. You can also implement it by hand, meaning that you don't need a computer to run your model. So somebody who doesn't know anything about statistics or machine learning can follow the tree diagram and use it to make a prediction. And lastly, it also mirrors the way people think. So you make your prediction or decision based on a sequence of rules. All right, and so what's the advantage of all these properties? So firstly, it allows you to audit your model for any errors or biases. All right, and then this also means that you can use the model in high-stakes decision making. Right, so in certain in cases like medical risk prediction or credit score prediction, so these are high-stakes decisions. You need to be able to explain the decision to your stakeholders. and then also to audit the model if there are any errors. All right, so this is yet another advantage of decision trees. And lastly, it's a very flexible prediction framework. And so decision trees, tree ensembles can be used in very diverse prediction tasks. All right, so this includes regression, classification, but also more esoteric problems like survival analysis, time series, multitask learning, causal inference, and more. All right, so it's very flexible. So in this talk, we'll focus on the most basic use case, which is regression. But the insights that we have probably do generalize to the other use cases too. Okay, so that we are all on the same page, let's talk about what trees are. What is a regression tree? Okay, so it's a piecewise constant model that you obtain from performing recursive partitioning of the covariate space. Okay, so let's draw a picture. So here we have 2 dimensions, and we have these data points that have 2 colors. Okay, so you can think of the color as the response. So we start with the constant model. So we predict the mean response over the entire data set, right? But we don't have to stop there. So we can divide the data set or the covariate space into 2 pieces. So we do a threshold on the feature x2 at the threshold A. And now we predict the mean response over each of these 2 pieces. All right, so this is also a model. And we can represent this by the decision stump on the right-hand side of the slide. But we don't have to stop here. We can keep going, and then we can further partition this piece at the bottom along x1 at the threshold B, and now we get 3 pieces. And again, we predict the mean response of each of these pieces. Okay, and so whenever you do this partitioning, you can represent the model in terms of a tree, and this is why this is called a decision tree model. All right, so I told you what tree models are. The next question is, how do you fit or how do you grow a regression tree? So the most straightforward approach that you can think of is to do empirical risk minimization, right? So standard approach in machine learning. All right, so what does this mean? So you consider the class of all tree models under some constraints, and then you devise a metric to measure the quality of each model. And then you identify the model that performs the best with respect to this metric. So unfortunately, this is NP hard in the worst case. And so in general, this is not a feasible optimization scheme. And so what people do instead is to use greedy algorithms. All right, so a greedy algorithm for learning a tree works by choosing the best local update at each step, and then it's iterative. So imagine that the current iterate that you have is this tree in the top left of this set. We draw a local neighborhood. Okay, so these are the trees inside this local neighborhood, and then we find the best model according to the metric in this local neighborhood. Okay, and then we make an update. We move to the next iterate. Okay, and we keep iterating. Okay, so now you draw a new local neighborhood, and then you do the same thing. Okay, so what algorithms do this? Okay, so the most popular one is called CUT. So this was invented by Bryman and other people in '84, but it's not the only algorithm. So there are many others that have since been invented and that are used by people. Okay, so I want to do a deeper dive into Bryman's CUT algorithm because this would be the object of analysis for this talk. All right, so imagine that we're at this stage of growing the tree. So we've made one split. All right, so the next step that we want to take is to split this, this piece at the bottom. So we call this piece of the covariate space a cell. All right, and then we want to make a split. So what is a split? A split is a tuple comprising the cell, which we call the parent, and then the 2 resulting cells that you make from the split, which we call the left child and the right child. Okay, so we have this, and right now this is a potential split, and we want to choose the potential split that maximizes some criterion. Okay, so what is the criterion? It's called the impurity decrease, and it's denoted as delta hat. All right, so this considers the split S, a cell, and then the data set that we use to impute quantities. Okay, so to compute this, we start by computing the residual sum of squares over the parent cell, and then we subtract the residual sum of squares in the right chart and that in the left chart. And then we normalize. So we divide this quantity by the number of observations inside the parent cell. Okay, so this quantity is called the empirical decrease. All right, so cut is when you choose a split that maximizes this quantity. Okay, so let me shift this up. So to interpret this, let's consider the population version of empirical decrease. Right, so this is defined as the conditional variance in the parents minus this weighted combination of the conditional variance and the children cells. All right, so as you have more and more samples, this empirical empirically decrease is going to approximate the population quantity better and better. Okay, so we can think of this as the reduction in residual variance for making the split S. Okay, so now what's a random forest? It's simply an ensemble of randomized cut trees. Okay, so how do we randomize? So here's the picture of the tree. So first, instead of fitting the tree on the original data set, we first draw a bootstrap resample, and we use this bootstrap resample to fit the tree. And then secondly, for every node, when we make a split, we first subsample the features, and then we choose the best split from amongst the subsample, right? And for every node, we draw a new subsample of features. Okay, so this is the randomization that we do. And now for random forest, we just do this b times. We get b trees, with every tree being grown with a different random seeds. And finally, we just add up all the predictions from all the trees, and then we normalize. So we take an average. Okay, so this is the random forest model. All right, so now we know what cut is, we know what random forest is, we know what empirical risk minimization is. So this leads us to the big question that we want to ask in this talk, which is there a statistical computational trade-off? Okay, so what do I mean by this? So let's consider the space of tree models, and then let's plot the training error landscape over the space. Okay, so the ERM obviously minimizes the training error. Cut is greedy, so you might get stuck in the local optima. All right, but of course we don't care about training error that much. What we care about is the test error. So the question is there a performance gap that you can quantify between ERM and cuts? Okay, we want to understand what this quantity is. Okay, so how do we do this? We need to find an appropriate statistical framework. Okay, so what is the right generative model to use to try to analyze this question? All right, so to do that, let's first take a look at what other people have done before. So what is the literature on theory for cut and for random forest? Okay, so generally, these algorithms have been analyzed in the statistics community. So there's a very heavy statistics
Sorry,
flavor to it.
do you mind if I ask a question?
Yeah.
And come back to your picture. Let's go back one slide. What are we comparing with? Are we comparing with the best possible test error, not the error attained by the ERM, right?
Oh, no, I'm comparing with ERM.
You're comparing
So
the
this,
ERM. Okay.
yeah, ERM versus cut.
Okay. Is there a reason to think that the ERM is the one that the best test error among
Not
possible trees?
necessarily. Yeah, not necessarily.
Okay. Okay. Okay.
But in some sense, it is so in our paper we also show this that using appropriate concentration, the test error of the ERM
Okay.
is
Yeah.
pretty good.
Yeah. Fair enough. Fair enough. Yeah.
All right. So so for previous results on regression trees, so this is mostly derived in the statistics community framework. And so the framing is that of non-parametric regression. Okay, so what's this model? So we assume training data set comprising IID data points, where the response for each data point is generated as some true regression function applied to the covariate plus some additive noise. Okay, and then xi, the covariate is drawn from some distribution on the covariate space. Okay, and then the regression function f star is contained in a known function class f. Okay, so we know beforehand what this function class is. All right, and we assume that the number of features is fixed, and then we let the sample size go to infinity, and then we see what happens. Okay, so here are the desired results that people aim for. So we want to have consistency in an L2 sense. Okay, so here we take the expected squared loss, where the expectation is over first x, so we integrate out the squared error over all points. We then take an expectation with respect to the randomness in the algorithm, and lastly, with respect to the training data set. And we want this quantity to go to 0 as you have more and more samples. Secondly, people care about L2 rates of convergence. So instead of saying that this goes to 0, we also want to quantify the rate at which it goes to 0. Okay, so these are the types of results that people have aimed for. All right, so what do we know? So first, for ERM trees, it's known that they are consistent when your function class has bounded covering numbers. So this was work by Abbe in 96. For cut, it turned out that it was very difficult to analyze. So for a long time, people were not able to really analyze it. The reason is that greedy algorithms are intrinsically pretty hard to analyze. So what people did instead was to study something else. So people started to study non-adaptive trees. Okay, so non-adaptive trees are trees that do not depend on the response when you fit the tree structure. Okay, so you can do this by completely randomizing. So that every time you make a split, you choose that split completely random. Okay, so that is a completely randomized tree. Alternatively, you could use a Mondrian tree, which uses some non-parametric Bayesian process to grow the tree structure. Okay, but again, it does not depend on the response Y. All right, so you grow the tree structure, it gives you a partitionally covered space, and then you take local averages. So this is the model that you get. And people were able to show that these models were consistent, and then they also achieved minimax rates under C1 conditions. Later on, people realized that you could actually derive consistency and rates for cuts, but you have to make more assumptions. Okay, you have to make certain assumptions that seem a little bit strange. Okay, so where are we now? And we want to check if these previous works have any say over the problem that we want to solve. Okay, so the first thing we observe is that there are no lower bounds. So all of these are upper bounds, right? So if you don't have a lower bound, you can't rigorously say that you have a performance gap. Secondly, something a bit strange happens. We can notice something strange from this literature, which is that non-adaptive trees seem to have better guarantees than cut and random forests, right? So we need more assumptions for cuts. They have slower rates. Okay, so this is pretty strange because in practice, nobody uses these non-adaptive tree algorithms. They are far worse empirical performance. So the takeaway is that this setting, this framing where you fix D and you increase and you let N go to infinity is probably not the right setting to analyze cuts or adaptive trees in general. Okay, so instead, we need to take a higher dimensional point of view. All right, so here we want to let both D, the number of features, and N, the number of samples, both go to infinity at the same time. Okay, and we're going to assume that the true regression function is sparse. So it depends only on some subset of feature indices of size S. Okay, we don't need to know what this subset is beforehand. So here's some notation. So we want to consider the expected squared error, where again, we take expectation with respect to these quantities. And now we introduce a definition. So we say that an estimator f hat is high dimensionally consistent if the following holds. So first we have the scaling regime. So n and d go to infinity such that the ratio of log n over d goes to 0. And then secondly, this expected spread error also goes to 0, okay, under the scaling regime. Okay, so this is the definition of high dimensional consistency. And so already in the literature, it's known that we have the following. So if we have sparsity of the true model, and then you also make some further assumptions, which I'll tell you about in a few slides, then we get high dimensional consistency using cut and or random forests. Okay, so this is work that you can find in these following papers. Okay, so let me give you a bit more intuition about high dimensional consistency. Okay, so the definition, I've just moved it up on the slide. Okay, so let's try to get intuition. We make this observation. So if you have n data points, then the average depth of the tree is at most log n. Okay. Yeah, there's a question, Alex.
Yes, I have a question about your high-dimensional consistency. Log n divided by d, that's new to me. So usually it's the opposite, right? Log d divided by n.
Yeah, so it's a very form of high-dimensional consistency.
Okay, so it's much weaker than what we usually use, right?
Yeah.
Okay, but it's not a typo. So okay, I wanted to understand this. Okay,
it's deliberately weak because in this work, we're interested in lower bounds. So the weaker, the more significant the lower bounds.
Okay, thanks.
Okay. Yeah, so if you have n data points, then n training points, then the average depth of the tree is at most log n. All right, because every time you make a split, you essentially take you essentially have the sample that you have, and then if you have you keep having log n times, you get 1 point. Okay, so what this means is that if f hat is high dimensionally consistent, under this scaling regime that you have for this definition, then the estimator cannot split on all features, right? Because you have fewer splits in your budget compared to the number of features. And so if you want to be high dimensional consistent, you need to be able to do appropriate feature selection of which are the relevant features and then distinguish them from the irrelevant features, right? And the fact that these previous results show that cut is high dimensional consistent implies that cut can perform feature selection given these additional assumptions that people have to make. Okay, so this is the intuition for high dimensional consistency. It's all about feature selection. Okay, and this is also reflected in practice. So back to this paper that I started to talk with. So they also perform some empirical investigation to try to understand why these tree-based models outperform deep learning. And so what they did was to take some real data sets and add some additional noise features. And what they found was that the performance of random forest and XGBoost under adding more noise features is pretty robust. Okay, so you don't do so much prediction accuracy when you add additional noise features. Whereas if you do the same for deep learning, the loss decays pretty rapidly. Okay, so let's go back to the topic of assumptions. Okay, so what assumptions do people need to guarantee upper bounds for cuts and random forests? So one such assumption is additivity. So here we assume that the true regression function f star can be written as a sum of univariate functions. Okay, so this was used in these books. And then another assumption that people made was that this one called sufficient empirically decrease, or SID for short, right? And so this assumption says that for any cell that you may have, if you look at the soup over all impurity decreases you get for possible splits on the cell is lower bounded by some lambda fraction of the conditional variance in that cell. Okay, so this condition was formulated by this first paper by Shuo et al. And the intuition behind this is that whenever you have some cell, we can always find a split of that cell that decreases the variance by a lambda fraction. Okay, so you can always make some improvement that's bounded from below. All right, so these are the assumptions that some of the assumptions that people make in order to derive upper bounds and consistency for cuts. All right, so our question is, are these assumptions necessary? Okay, so we're going to analyze this question in the context of binary covariates with the uniform distribution. Okay, so obviously this is not realistic, but it gives us a setting where we can have very clean calculations, and this allows us to get at the essence of what's happening with cuts and other greedy methods. Okay, so here's an easy example. Okay, so we consider the exclusive OR function, or XOR for short. Okay, so under binary covariates, it can be written as the product of x1 times x2. Okay, and so such a function is going to be difficult for cut to learn. And this is sort of folklore, so this was known already, and this is discussed in some of the previous papers. Okay, so here's a representation, a visual representation of this function. Okay, so it takes the value 1, and when x1, x2 are equal to 1 or -1, and then when they have different values, it's equal to -1. Okay, so what happens? So for the entire covariate space, okay, so if you think of this as these as classification, okay, so this is, we're considering regression, but the function, you can think of this as giving you the class of each data point. Okay, so there's a 50-50 class split over the entire covariate space. So now if we try to split on a meaningful feature, which is x1, and we consider the right chart and the left chart, in the left chart, there's also a 50-50 class split. And then in the right chart, it's the same thing. So if we make a split on x1 and we compute the empirical decrease, we get 0. Okay, so we make no progress. Okay, there's no reduction in variance when we make the split. And you can show that for any feature that you may consider, the empirical decrease in expectation is equal to 0. But not just that. Okay, so this is for the entire covariate space. So what you can show is that for any cell that you can that you may achieve, when you grow the tree, the empirical decrease with respect to any feature is equal to 0, unless the cell has already split on x1 or x2. All right, so you cannot make progress unless you already found the solution. Okay, so this is a chicken and egg problem. All right, so we call this phenomenon a marginal signal bottleneck. Okay, so for reasons that will become clear later. Okay, so it's a bottleneck, and it occurs because of the fact that cut uses marginal quantities to make splits. Okay, so as a result of what we just discussed, cut is going to make completely random splits, essentially. All right, so it's like a non-adaptive tree at this point. And so because of that, it's not high dimensional consistent. All right, so this was folklore, but until now, there was no formal proof. And furthermore, it was essentially the only example that has been discussed. And there's no generalization beyond this. And so in this work, we addressed these issues and also did a lot more than just that. Okay, so that's what we're going to talk about right now. All right, so how do we generalize the XOR function? Okay, so first, let's ask the question, why is XOR so hard to learn? Okay, so it is a pure interaction, right? So pure interaction means that there's no marginal information, which is essentially what we saw just now. On the other hand, cut uses only marginal information to determine splits. All right, so what does this mean? So consider a data set that is represented in this table. Okay, so the columns are the features, and then I also included the response over here. Okay, let's forget about the noise for the moment. When you want to compute the empirical decrease with respect to the first feature, x1, then the only part of the data set that's being used to compute this quantity is the portion that I've circled in orange. All right, so everything else is thrown away, it's forgotten. All right, so this means that instead of using the joint distribution of all the covariates, we're using the marginal information, just x1 and the response, right? And you can see that under the uniform measure, x1 is independent of y, all right? So there's this conflict between the way in which curve is selecting splits and the behavior of the response in this generative model. All right, and then if you want to spin x2 and then we compute this empirical decrease, it's the same thing. Okay, so again we use this marginal information instead of the joint information. Okay, so let's try to generalize this. So 1L is a pure interaction. Okay, so the Zoll function was x1 times x2. So there was a Boolean monomial. Okay, so other Boolean monomials, there are also other Boolean monomials, and these are also pure interactions. Okay, so more precisely, take any subset S of the feature indices, and consider the product of xi, where I ranges in the subset. We denote this by chi sub S, so this is a Boolean monomial. So these are further examples. It turns out that this is that Boolean monomials are quite generic. So if you consider all functions on the Boolean cube, it can be represented as a linear combination of Boolean monomials. Okay, so Boolean monomials form a Fourier basis for these function space. Okay, so any function f has this unique decomposition. All right, so now that we know we have a sense of what possible functions may exist, let's look at some definitions. Okay, so in a series of papers, Emmanuel Abbe and his collaborators came up with these definitions. Okay, so this was not in the context of trees, so this was in the context of neural networks. And we're going to draw a connection later on. All right, so first, let's just understand the definition. Okay, so given the function that is written in terms of this Fourier basis, we say that it has the staircase property if you can order the index sets as follows, x1 to xk, such that we have this sequential inclusion, and so that the first subset has size 1, and every subsequent subset only contains one additional index compared to the previous. All right, so this is called the staircase property. So here are some examples. Okay, so if we have the function x1 plus x1 times x2, okay, so this is a staircase function. Here are some counterexamples. So if we have the Zoll function, okay, this is not staircase because we jump from 0 to set size 2. And then similarly, if we have x1 plus x1 times x2 times x3, this is also not a staircase function. Okay, so it's a fairly natural definition that reflects some hierarchical structure. However, it turns out that this is not the most appropriate definition. The most appropriate definition is that of the merged staircase property, or MSP for short. So this generalizes the staircase property as follows. So again, we have this ordering of the index sets, but this time we don't need sequential inclusions. What we need instead is that for every index set S sub j, okay, if you take the difference between this and the union of all the previous subsets, we only have one additional point that we add to it. Okay, so this is called the merged staircase property. So again, some examples, right? So some counterexamples first, right? So the same counterexamples for staircase are also counterexamples for merged staircase. Okay, so each of these cases, we have a jump of size 2. And for positive examples, okay, so this first example satisfies the staircase property, also satisfies MSP. And then we have a new example, so x1 plus x2 plus x1 times x2 times x3. Okay, so this also satisfies MSP. All right, so with this definition, let's go to our main results. So I reproduced the wording of the definition at the top of this slide. All right, so here's our theorem. So suppose the regression function f star depends on only S covariates. Then we have the following. So first, MSP is necessary. So if f star does not satisfy MSP, then this expected squared error is bounded from below by some constants whenever the number of samples that you have is less than some exponential in the dimension. Okay, so this is a very severe result. Right, so you need exponentially many sample. So the sample has to be exponential in dimension in order for you to learn a non-MSP function. And then we also have near sufficiency. So if the function satisfies MSP and the coefficients are generic, okay, so generic means up to a set of measure 0, then this expected squared error is bounded from above by 2 to the s times log d divided by n. Okay, so to learn such a function, we just need 2 to the s times log d samples. Okay, so the separation is exponential and logarithmic. So it's a huge, huge separation. And then furthermore, okay, so this was for cuts. So now let's see what happens for ERM. So regardless of whether f star satisfies MSP, the expected squared error for ERM is again 2 to the s log d divided by n. Okay, so let's try to represent these results in the form of a table. Okay, so my left column is MSP, my right column is non-MSP, and then I have cut and ERM. Okay, so I also throw in non-adaptive trees that we talked about earlier. Okay, so what are the takeaways? So first, we have a statistical computational trade-off, as promised in the title of this talk. So when we consider non-MSP functions, we have this performance gap between cuts and other greedy methods actually, and ERM. Okay, so this is the first takeaway. The second takeaway is that for cuts, we can actually characterize the regression functions for which cut is high dimensional consistent. Okay, so if it is MSP, then it is consistent. If it's non-MSP, then it's not consistent. Okay, so this is a complete characterization. Okay, before I go there, and the third thing is that if you consider non-adaptive trees, so they always require exponential dimension number of samples, right? So it seems that for MSP functions, the behavior of cut is closer to that of ERM, and then for non-MSP, it's closer to that of non-adaptive trees. All right, and then some remarks about the generality of our lower bounds. Okay, so first, they hold more broadly, so not just for cut, but also for random forests and other greedy trees and ensembles. Secondly, even when there's no noise, the lower bounds hold. Okay, so this is all about bias, nothing about variance. And thirdly, we have some robust versions. So even when the true regression function f star is MSP, we can obtain some lower bounds that depend on how far the function is from being non-MSP. Okay, so we make these lower bounds robust. Okay, and then we have a surprise. And we have the surprise that we didn't anticipate when we first started doing this work, which is that with our results, we can actually perform a head-to-head comparison of neural networks. And as far as we are aware, this is the first theoretical head-to-head comparison of random forest or other decision tree methods against neural networks. Okay, so let me say a little bit about some recent work in the neural network community. So obviously, there's been a lot of work on the theory of neural networks, but the recent wave has this focus, which is quite different from what came before, which is that they're trying to understand this question, which is what types of functions are learnable by two-layer neural networks that are trained using SGD. Okay, so previously people analyzed approximation, ERM neural networks, or without any sampling properties or sampling issues. Okay, so this wave of work tries to be more realistic, and so they try to analyze neural networks as they are trained in practice. Okay, so as you can see, there are lots of very recent papers in this direction. Okay, of special interest is this first paper by Emmanuel Abbe and his collaborators, in which they defined the merge stack as property. So what they did was to study, again, binary features. And then, so this was binary features as the generative model. And the algorithm that they studied was a two-layer neural network that was trained using online SGD in the mean field regime. Okay, so what is the mean field regime? This is where your neural network is fully connected, it's very large width, and then you run SGD with a constant step size online, which means one sample per iteration, one new sample per iteration, and for only all the iterations where D is the dimension. Okay, so why is this called the mean field regime? It's because for this regime, and up to all the D iterations, the dynamics of SGD can be approximated by this nonlinear PDE. All right, so what were their results? Okay, so they showed that the same definition, this merge stack as property, also characterizes learnability for two-layer neural networks under this mean field regime. Okay, so again, necessity. Okay, so F star is learnable if it, okay, sorry, I think I made a typo. Not learnable, F star does not satisfy MSP, and then learnable, F star satisfies MSP, and then generic. Okay, so it's a typo here. Right, so you can see that there's a very close similarity between this mean field regime neural networks and greedy regression trees. Okay, so let's go back to the table and supplement this with this new result. So we have this new row in this table, and we see that for MSP, okay, so two-layer neural networks can learn two-layer neural networks can learn this function with all the samples, and for non-MSP, we need more than all the D samples. Okay, but there's more to this story. Okay, so that was the state of the literature until perhaps sometime last year. So more recently, people tried to analyze what happened beyond the mean field regime, which is you have to run SGD beyond all of the iterations. And what these two papers found is that if you run SGD for a long time horizon, you can actually learn k-order monomials with this order d to the k-1 samples. Okay, so remember that for greedy trees, this was exponential indeed. And here we get order d to the k-1. Okay, so after that, or maybe slightly before that, so Abbe had a new definition conjecture. So here, so this is to supplement definition of MSP. So he said that the function has leaf complexity k if, again, in the same fashion as MSP, we have this ordering of the subsets, of index subsets, and the step size that you get for every new subset is at most k. Okay, so this means this is a definition for leaf complexity k. All right, so here's an illustration. So we take the set of non-MSP functions, and then what this new definition does is to break it into pieces. Okay, so this is now decomposed into leap 2, leap 3, and then so on and so forth. Okay, and then MSP functions are leap 1 functions. Okay, so this is the new definition. And what he conjectured was that the sample complexity for learning a leap k function is order d to the minimum of k-1 and 1. Okay, so this is the new conjecture. So we put this into the table. Okay, so now we expand the columns in this table. So non-MSP has become leap 2 up to leap k. And then for two linear neural networks, under this conjecture, if this is true, then we see this sequence of sample complexities where we always increase by a factor of d as you increase the leap size. But regardless of the leap size, for these decision tree-based estimators, we don't see any difference in performance. Okay, so cut is still exponential dimension, ERM is still 2 to the s times log d, non-adaptive is still exponential. Right, so assuming that this conjecture is true, we get this comparison between two linear neural networks and cut, random forests, and other regression tree algorithms. Okay, so now let me give some intuition about how we proved our lower bounds. So why are lower bounds hard? Okay, so let's return to the XOR function. Okay, so how would you try to prove a lower bound? So here's a naive strategy that one would take. Okay, so you want to prove that cut will never split on the relevant features, x1 or x2. So how do you do this? Okay, we use concentration. So cut makes splits based on the empirically decreased value. We know that in expectation, all of them are 0. So what we need is to get concentration for the empirically decreased values. Okay, so we need this. Okay, so this deviation, we want it to be order n to the -1/2. Okay, so this is true. So you can show this fairly easily with some basic concentration inequalities. But the problem is that if you want to use this to show what we want, which is that cut never makes these splits, we need to do this uniformly. So we need to show concentration for all possible splits. Okay, so this is now a supremum over all cells and all features K. Right, and this is too ambitious. So this is not even true. Okay, so this approach doesn't work in giving you the lower bound that you want. So what we would do instead, okay, our new strategy is to do something else. So we're going to consider a single root to leaf path of cut. Okay, so this means that we fix some query point x, okay, like a test point, and we consider the root to leaf path taken by this query point in the tree that's grown using cut. And we're going to show that this root to leaf path never makes a split on x1, x2 with some probability. Okay, and so this gives you a new interpretation of cut, this root to leaf path as a stochastic process. Okay, so we're going to use some ideas from stochastic process theory. And how we're going to prove this, we're going to use coupling trick and then some symmetry arguments. Okay, so this is the high-level view of how we proved the lower bounds. Okay, so let me talk a bit more about this root to leaf path. So let's start with the entire covariate space and this query point x sub 0. Okay, so this is denoted by a node. Okay, we're going to make this into a tree. Okay, and let's denote this cell as C0. Okay, so now we make a split into two cells. We only care about the cell that contains the test points. We call it C1. And then we keep going. Okay, we make a further split, consider the cell that contains X0, and we call it C2. And then we keep going down this root to leaf path. All right, so how do we formalize this as a stochastic process? So the depth of the cell is the index, the time of this process, time index. And the observations at the time index are these empirically decreased values. Okay, so you can think of this as a sequence of vectors. So now the quantity that we're most interested in is what we denote using J. Okay, so query point x0. Okay, so this should be an x0. So we used J of X0 and the data set D to denote the set of features that are split upon along this root to leaf path. Okay, so this is a subset of all the feature indices 1 to D. All right. So it turns out that we can reduce this lower bound, reduce the problem of getting a lower bound to bounding to giving giving a bound on this probability that the relevant features are not contained within this root to leaf path index set. All right, so how do we do this? So very quickly, so we start with the expected squared error, right? We use the tau property to write this in terms of the conditional expectation, where we condition on the values of the covariates for all features apart from x1, x2. Okay, so just tau property. Then we insert an indicator. Okay, so we insert an indicator of the event that this feature set does not contain the relevant features. Okay, so we can always do this, and then we get a lower bound. And now something interesting happens. So on this event that the root to leaf path does not split in x1, x2, then the prediction f hat is constant with respect to x1, x2. It doesn't split on these features. So if this is constant, then this conditional expectation is simply equal to the variance of f star. Right? Because you have a constant model, and when you take this expectation, you integrate out the distance of the true function with respect to a constant. Okay, so actually this should be a lower bound. Okay, and as a result, we lower bound, we can continue this calculation, and then we get a lower bound, which is so the variance becomes we replace this conditional expectation with a variance term. Right, and then taking the variance out of the expectation, we get the variance of the function times probability that this root to leaf path does not split on x1 or x2. Okay, so we have reduced the problem to getting a lower bound on this probability. All right, so how do we bound this probability? Okay, we're going to use the idea of coupling. So we consider the stochastic process that we introduced earlier, which is the root to leaf path. So what we want to say is that this path splits on a random subset of features. Okay, so it splits completely at random. And if it splits completely at random, the probability that it splits on x1 or x2 is going to be very small. It's going to be order 1/d. Okay, so in general, this is not easy. So this is, in fact, pretty hard to show. So we're going to use a coupling trick, which is the following. So we're going to construct a related path, which I denote as C0 with the superscript 1, and then so on and so forth. And then we're going to couple this new path to the original stochastic process. Okay, so we're going to prove that this related path has the desired property, which is that it does this it splits totally at random. And then we're going to show that these two paths are similar with high probability. Yeah, and that's going to complete the proof. So there's a question, I think, but I can't see the chat. Oh, okay. Yeah, so, okay, so I'm at my last slide, actually. Okay, so here's the high-level takeaway. All right, so when we do machine learning theory or statistics theory, so most people like positive results or upper bounds. Yeah, so you can think of this as the character from the movie Inside Out. Okay, so these results tell you that our algorithms work, they perform well, but sometimes it's also useful to have negative results. Okay, so why? So in our case, they tell us how to compare our algorithms with other methods. Okay, so in our case, when we should use other methods instead of regression trees, ensembles, or in this case, greedy regression trees and ensembles. Secondly, they also tell us how we can improve these algorithms. So sometimes some of these weaknesses, they don't need to happen. Okay, so there are ways in which you can fix these weaknesses. Right, so in this talk, what we have shown is that if you use greedy optimization to fit regression tree models, we have some limitations. Okay, precisely when we have these non-MSP functions. Okay, but yeah, so this is the topic of this talk. In general, and in my work, I have also looked at some other negative results. So here's just a little preview. So I also have some work on the limitation of tree representations, and also some work on Bayesian trees. Okay, and with that, I shall end the talk.
Okay, all right. Thank you, Yanshuo. Very, very interesting talk. Questions from the audience? All right. If not, I'm going to ask some questions. There's very interesting connection between this Fourier analysis and then as well as sort of like this, shall I say, hardness of being able to learn this function. I just wondering, let's say given a data set, is there some way of saying like, perhaps from the Fourier series that somehow it's this particular data set that's suited or not suited for decision trees or that kind of thing, or maybe.
Yeah, so okay, so good question. So my perspective is that this work is mostly theoretical.
Yeah.
The takeaway for a broader audience is not so much the specifics of MSP versus non-MSP, but that there are certain issues that do exist when you use greedy optimization.
Mm-hmm.
And the bigger principle or the more general principle is that when you have these very weak marginal structure that's hiding some very strong interactions, and you probably don't want to use
Right.
greedy.
I see. Okay, earlier you also mentioned a comment about this cut versus non-adaptive things. Maybe you could tell us a bit more about. They said there's some regime and one is better than the other. Maybe
Yeah. So let's okay. Let's go back to that slide.
Yeah.
All right. So then there's this one. Yeah. So if you perform a classical analysis, a classical non-permanent regression analysis, which means that you fix the dimension, you let the normal simplest go to infinity, and then you try to get some upper bounds for non-adaptive trees and for greedy trees.
Yeah.
You find that you can get better results for non-adaptive trees.
Right.
Okay? So some of this is some of this is a limitation of analysis. It's because of the some of it is limitation of analysis because it's certain aspects of this are worst case versus average case. So in average case, greedy trees might work fairly well, but in the worst case, it could be fairly bad.
Okay.
So that is some part of it.
Right.
But it's also true that you can be quite suboptimal if you use greedy trees in such a setting.
Fair enough. Okay. Any other questions from the audience?
I have one more question. So you now have this model of functions where decision trees do not work, the MSP functions. And the reason for that is that you do this greedy optimization. Do you have any intuition on if we can do it like slightly non-greedy and get something which works then also for these functions with you had this class of functions with different step lengths, basically, where the two-layer neural networks worked. Do you understand my question?
Yeah. So are you asking, is there a fix that you can?
Exactly. Yes.
So the answer is yes. I don't know whether I can quickly go to that slide. So the answer is yes. And let me try to find the appropriate slides. Okay, let's use this slide. So you can actually fix this by being even more greedy.
Mm-hmm.
So the problem with cut is that it does a one-step look ahead, right? So it looks at the marginal information, which is one feature, and then it decides the best split according to this empirically decrease criterion. Now, if you did two-step look ahead, so instead of saying what happens if you make one split, but instead look at what happens if you make a sequence of two splits, then this would allow you to essentially learn step two functions, right?
Yes.
But if you have leap tree, this leap K definition, right? So if you have leap tree, then a two-step look ahead is going to fail. Okay, so you always need to extend the look ahead to handle leap K functions of bigger K.
Yeah, and I guess the cost of performing too greedy is, I mean, it grows exponentially in the leap size.
That's right. Yeah.
Yeah, but still, it's nice. It's nice.
Yeah. Good question.
All right, I think we will stop here to be past past the hour. Thanks a lot to everyone who's here, and have a good Christmas and Happy New Year. And we'll start again next year. Right. Bye bye.